The good thing about having a talk at the end of a workshop is that you basically can skip all of the introduction. Yeah, I'm working in Munich together with Till and Joanna on dust coagulation. And since this is a numerical workshop, I thought I spent a few minutes to introduce a code that we've been developing in the last few years. It's basically how does dust evolve in a disk? How does it grow, and how does it accreted? And so we developed a Python package. It's called DustPy that just does that for us. And the output of DustPy is basically what you see here. You've already seen these kind of videos several times in this workshop. On the x-axis, you have the distance from the star. On the y-axis, you have the particle size. And in the color-coded is just the density distribution of a certain particle size at a certain radius. There are also several other lines in this plot. The white line corresponds to particles of Stokes number 1. The blue dashed line is the fragmentation limit. So you will see when particles reach that blue line, they will fragment. And the green line is the drift limit. So when particles at the green line drift faster inwards than they can grow. That means at the green line, the speed into the left direction is larger than the speed in the upwards direction. And if I let this run, it has a wide what? Here. Yeah, you see growth starts in the inner disk because the densities are higher, the timescales are just shorter. And you have an inside-out growth. As soon as the particles reach the fragmentation limit, the smaller particles are replenished. And when the dust gets accreted, the drift limit comes down, and and you only have the particles close to the drift limit and no small particles. So the good thing for you maybe is that this code will be public soonish, as soon as the main developer finished the documentation. And the idea or the philosophy of that code is that everything is modular. So you can replace anything in the code with your own subroutine. So if you want to have anisotropy in alpha, you can just implement that, or other different effects. Or if you just want to use the code to update your coagulation videos on your slides, you could also use that. Okay, but now dig into science. You may notice one problem. At the end of the simulation, there's barely any dust left. And the end of the simulation here is 10 million years. Already after 1 million years, there's 90% of the dust gone. And after 10 million years, there's 99% of the dust gone. But we still see dust disks at that age. So something has to happen. And it was already quite old, a paper from 1972 that proposed, okay, if you have a pressure perturbation, you can trap dust particles in that perturbation. And then I skip 40 years of research onto that. Paula Pina used an earlier version of the code, and she just added sinusoidal pressure perturbations on it, and that actually could help, and you could retain dust for the required lifetime. So that was basically meant as a proof of concept, because in 2012, this looked like that. So this is TW Hydra, and it looked just smooth. And but 4 years later, we suddenly have that image, and also notice there's a difference in scale and resolution. So disks have some substructure, so something is happening. And this plot was also shown quite often. Or the D-sharp survey showed lots of rings, so there is something going on. And in K's D-sharp paper, he looked into 8 of these dust rings in a closer detail. And he summarized the results. And basically what he did is he was fitting Gaussian profiles to the intensity. And so he could get basically the width of these Gaussians. And with some convolution theorem, you could go back to what is the width of the dust rings in that. And he summarized that in this nice table. I just wanted to highlight these 2 columns. So what you see here in column 14 is the width of the Gaussian compared to the beam size. They are all larger than 1, so meaning the dust rings are resolved. The second one, the width of the dust rings compared to the pressure scale height. The idea behind that is, if you have a perturbation in gas, the minimum size it can have is the pressure scale height, otherwise it wouldn't be long-term stable. And what you then see here is if you compare the dust width with the minimum size, some of those rings are smaller than the pressure scale height. So that is an indication for dust trapping. And Till already showed that plot. It's basically the summary. All the data points that are larger than the green line are resolved. So all of them are resolved. And all of them that are below the yellow line, they have for sure dust trapping. And yeah, one of the, I think, most surprising results of these rings is that all of the optical depth in these rings have roughly the same range. None of those rings is completely optically thin, but it's not surprising because there's a bias in the rings that I've chosen. So they are the more massive, brightest rings, so they are for sure not optically thin. But none of these rings is optically thick. And why is that? So it's still a low number statistics here, but it might indicate that there's some physics behind it. And last week, there was the conference in Victoria, and Enrique Macias showed results from another disk, it's another HD phone number. And also here, the optical depth that he gets out of his observations, they are in the same range. So I just plot this now. Also in that plot, I just omitted the error bars here because I'm not sure about them. They're all in that range. So something is going on there. So the idea is we want now to, put this into DustPy and check what is going out of there. So the idea is we want to model the second ring of HD 163296. To do that, we need to have some kind of pressure trap. And we could either have a pressure maximum somewhere, or we can induce a gap, and then we have in the outer edge of the gap, we have also a pressure trap. But we do not want to fix the gas, because we also want to evolve the gas. So the idea what we want to do is, in steady state, the surface density times viscosity is a constant. So if you want to have a gap in gas, we have to increase the viscosity. And since we are using the alpha prescription of viscosity, we just have a Gaussian gap, Gaussian bump in the viscosity, so we get a gap in the gas. And we used these kinds of values for that. And at that point, I'm completely agnostic what is causing the gap. So it could be a planet, but as you see here, it's just also a perturbation in alpha. And it's a bit cryptic here from these values, but the maximum perturbation in alpha we have here is a factor of 7. So if you have some MHD simulations, you have a factor 7 perturbation in alpha that could also create something like that. The parameters of the star are here. It's like a 2 solar mass star, and the disk mass, the initial disk mass, is about 15% of the stellar mass. Okay, and for the post-processing, we use the same opacities as in the D-sharp sample. This is how the simulation looks like. It's basically the same as before, but now we have a gap in gas that's evolving here, and in the outer edge of the gap, we have our dust trap. And at the end of the simulation, all the particles are drift limited, except for in the gap where they are fragmentation limited. And if we now look at the optical depth in the peak of this dust trap, it looks like that. The shaded region and the arrow bar are the observation of the D-sharp sample, and we are way above that. So we have 5 times higher optical depth than the D-sharp survey showed us. So the problem is we have too much mass in that ring. So we thought we have to remove some mass, and since this is a large dust accumulation, maybe there's planetesimal information. So just, let's check what happens there. So we need a prescription, and we started with something simple, what also Tokyo Skoneberg and Chris Ormel did. We trigger something when the midplane dust-to-gas ratio is larger than 1. We heard just earlier that might be not the case, but if you come up with something better, just let me know and we can put it in. If that is the case, we trigger some planetesimal information, and we just remove pebbles and put them in planetesimals, depending on their settling timescale. And the settling timescale is the Stokes number, so the large particles are removed more efficiently than the small particles. We put that into our model, and now we have that. What you see is that you don't see anything different than before. It looks almost the same, but if we look at the optical depth, now suddenly, as soon as we have a midplane dust-to-gas ratio of 1, we trigger our planetesimal formation, we remove dust, and we are basically, for the rest of the disk lifetime, we are in the range that the D-sharp survey is just observing. If I plot the the midplane dust-to-gas ratio, you see that also here. As soon as we reach midplane dust-to-gas ratio of 1, we just remove dust that we basically stay at 1, and that's why we have an optically thinner ring. But what we actually fitted was the intensities. So it's also here. It's the intensity profile that is measured, and after about the age of the disk, we roughly reproduce the intensity profile. We don't reproduce the wings, but as you see here, there are other features in the disk which we did not put into the model. So there are several rings. So next step is also to check if we have several rings, if you can get closer to the actual observed profile. And here's the mass budget of gas in purple, the total dust, the dust in the ring, and the planetesimals. That's the data point from a D-sharp sample, but since we recover the same intensity and use the same opacities, we also have the same dust ring mass. But what's interesting here, the planetesimals in the ring, these are 400 Earth masses. That's quite massive, and it's in a tiny ring. But also have to say, we did not evolve the planetesimals at all. We just let them stay where they were produced, and there was no scattering, nothing, just kept them there. Okay, to summarize, we checked what happens when we have dust trapping in rings, and we also then implemented planetesimal formation, and turns out this is self-regulating because we have a threshold for midplane dust ratio of 1. If we are larger, we remove dust, and if we are smaller, we can accumulate dust. So it will stay at this value of 1. And it can reproduce these fine-tuned optical depths that we see there. The question is, what are alternatives to that model? So we were also looking into back reactions. So Matthias Karate, who is a PhD student of TIL, implemented back reaction into DustPy, and we will check if the back reaction can also smooth out concentrations without even the need for planetesimal formation. And also what we heard earlier, Xiaowang Xu had a paper recently about scattering, that if you don't have scattering, or let's say if you have scattering, optically thick disk can look optically thin. That wouldn't work in our case here because our dust particles in the ring are centimeter sized, so 3 centimeter sized. But for this to work at that wavelength, you need 100 micrometer sized particles. But I think both ideas are complementary because if you have 100 micrometer sized particles, you don't trigger planetesimal formation, but you still have that kind of optical thickness. But yeah, in the future, we want to check multiple gaps. Do all the other gaps also have the same range and optical thickness? And also, we want to check or scan through the parameters. Can we break this somehow? Can we have, even if we have planetesimal formation, can we have different optical depth? And also, what happens to the planetesimals? Because we have a quite massive ring. And but there are also observations of debris disks that have quite massive planetesimal dust rings, but they are a bit wider than in our case, but we didn't evolve them any further. And also, planetesimals, something happens to them. Maybe they collide to embryos, and then we have pebble accretion onto these embryos. That's also what we already did, just a little sneak preview. We took Chris Ormel's analytical formulas for pebble accretion and plugged them into DustPy, and we put 2 embryos in the model, one at Jupiter and one at Saturn location, which have 1% of the Earth mass as initial mass, and we let them just accrete. What you see here in the fine white lines are contours in Stokes number, so 1, 10 to minus 1, 10 to minus 2, 10 to minus 3. And as soon as the particle distribution reaches the 10 to minus 1 Stokes number, we start to accrete onto the embryos. The dashed lines here are the pebble isolation masses. So you see, basically, Jupiter can open a gap. It's also what you see at the end of the simulation here. But Saturn cannot, because the disk is already depleted when Saturn starts to accrete. Okay, with that, I'm at the end of my talk, but I still have a few minutes time, so I wanted to show a bit how DustPy actually works. So how, if you want to use it, how would it work? Since it's a Python package, you just basically import the simulation module from from DustPy, and from there the class simulation. Then you create an instance of simulation. So at the second line, S is now just an empty simulation object. Everything is none in there. When you then initialize it, DustPy checks everywhere where it's none. It just puts some standard parameters in it. And then afterwards, you have a simulation that is ready to go, and you just put evolve, and then you get basically that model that you had earlier. So it was 4 lines of code. If we want to put some physics in it, let's say we want to have an ice line. Let's say inside of the ice line, we have a fragmentation velocity of 1 meter per second. Outside of the ice line, we have 10 meter per second. Yeah, then we have to create a function that's doing that for us. So we just define as a function vfrag. It needs the simulation object as input. And we say, okay, everywhere where the gas temperature is smaller than 150, we have 10 meter per second, so it's CGS unit. If it's inside the ice line, 1 meter per second fragmentation velocity. Then we do the same here. We import a simulation class. We have a helper class bind function, and we import the vfrag from here. We do the same. We create the instance, which is at this point empty. But in the empty class, we bind into S our vfrag at the position of the fragmentation velocities. We do initialize. Now DustPy knows, okay, it sees now there's the fragmentation velocities. So it only replaces all the rest. And then we evolve it. This is now 10 lines of code, and you have something like that. And you can basically do anything what you want. You can replace anything. And all the models that I showed you were less than 50 lines of code. So you don't have to deal with a stupid Smoluchowski equation, and yeah, can just change the physics. Okay, thank you.
Thank you. Questions? Yes?
Like you have Stokes regime in your disks, is that true? Does it transition to Stokes? In one of your early simulations, you have a turnover at like 10 to the minus 1 AU.
That one.
Yeah.
Exactly.
Oh, great.
Okay. Other questions? Yes?
The primary developer expect to finish the documentation, and may I urge that person to feel free to release a preliminary version without complete documentation that can continue to be improved.
I tell him.
Okay, are there other questions?